Start again.
Okay.
Actually, I was trying to find out which one was it, but I don't know. I couldn't. Okay. Hi, everyone. I'd like to give a talk today on using mathematical models for better understanding flight estimation methods currently being used. As you all know, the floods are a recurring natural threat in many areas in UK, even in Bath, as you can see on this photo taken during a flood event in 1960s. And many models were developed to allow us to assess the flood risk in given areas. The fundamental questions that those different models need to answer, which is also a fundamental problem in hydrology, is to predict what is the peak flow that we observe in the river after an intensive rainfall of given intensity and duration, like the one that we have today. This is illustrated by these so-called hydrographs. And this problem mathematically is like very complex, also from a physical point of view, because the flow is generated both by the overland flow and the subsurface flow, which are coupled together with each other, and both the topography of the terrain and the spatial structure, hydraulic structure of the soil and the parent material, bedrock, is very complex, which makes this problem very difficult to handle. So during today's talk, I will briefly introduce you to the models that are currently being used and what are their limitations. Then I'll try to address these problems by investigating what are the key parameters that are used in those models. What is the scale of those parameters in UK? I will try to standardize our knowledge at this point. And based on this analysis, based on data, we'll build a benchmark model which will be representing which will give us some simple view, a simple benchmark model to work on, which is representing the complexity of the real world systems. And using non-dimensionalization and asymptotic methods, I'll show how can we reduce this model to simpler forms. And finally, I'll show you that at some scenarios, we can even find an analytic solution describing the hydrographs, like the one showed on the graph on the previous slide. And I'll finish the talk telling you a little bit more about possible future work. So let's start by looking at the models which are currently used. Those models can be divided into three main classes. We have the physical models, which are based on laws of fluid dynamics, which are describing the subsurface flow and overland flow using PDEs. But those models, first of all, required very detailed spatial data to be used about the area that we want to model. And secondly, they are computationally expensive. That's why in hydrology, very often conceptual models are used instead, which represent also the same physical processes, like like separation of the flow into the surface flow and the subsurface groundwater flow, but they formulate it in much simpler way. For example, by assuming that the flow, like the groundwater flow, is proportional to the total amount of the water which is accumulated under the ground, which forms some simple dynamic systems that we can work with. And finally, last but not least, we have statistical models, which are ignoring all the physics or are not looking at the physics behind the processes, but instead aim to find a relationship between the data that we have available about the area that we want to model. For example, the area of the catchment. Catchment is, of the river basin. Or we may have data about the rainfall in a given area or about the soil properties. And we can extract some statistical properties of the flow in the river, such as what may be the expected maximum flow that we observe every year in a given area. So there is another property of this landscape that I try to illustrate with this chasm, which I call the chasm of ignorance, just representing the fact that even though all those different types of models are predicting the same quantity, the flow in the river, they are based on different assumptions, quite often contradictory with each other. And as a result, this modeling approach will give different predictions. And so this is the observation that I've made at the beginning of this project, and it's consistent with the criticisms that you can find in the literature. And here are the three main points that I want to emphasize based on the literature review. So first of all, a lot of models have been constructed in the last 60 years since the first conventional Stanford watershed models. And they are often developed independently by different institutions. So for example, research groups which are working on database models, statistical and conceptual models, will hardly ever are hardly ever involved in a physical modeling. And the researchers who develop physical models are not using the simplifications done by other types of models. And also, even the models between different countries will differ. So different models will be used in UK and USA. This is not as standardized field as, for example, fluid dynamics in mathematical community. Secondly, the model assumptions and constraints are not critically assessed when formulating the model. What is being tested is the outcomes of the model, but not the assumptions themselves. So, and we can test only the outcomes of the models based on the data that we have available. But we have no information about the limits of applicability, whether we can apply our models in a different situation than the one captured by the data on which we tested them. And finally, which is a consequence also on the second point, the predictions of those models are sometimes highly inaccurate when you apply them for the data which are underrepresented in a training data set. For example, if we try to apply a model calibrated on one catchment to another catchment, or for example, they're calibrated on the usual rainfall to an extreme rainfall. This was a high problem. This is very nicely captured by James Kirshner in the abstract of his work from 2006. He said that advancing the science of hydrology requires not only developing theories that get the right answers, but also testing whether they get the right answer for the right reasons, so that we know that we can apply those models even in unusual situations. So something that also very surprised me is that there are hardly any or almost no works from the mathematical community, from mathematicians, which would try to address the problem of formation of the flow as a result of both the groundwater and the surface flow. Usually there are a lot of works on the groundwater flow, on the flow through the porous medium. There's a lot of works on shallow water screening, disqualifying the overland flow, but there are hardly any rigorous studies on coupled flows with both of these two flows coexisting and interacting with each other. And this is a gap that me and Phil decided to fill as a part of my PhD. Namely, we proposed an asymptotic framework that may allow us to compare different currently used models and assess what are the possible sources of their inaccuracy on this fundamental level. So as the first step, we want to identify the key physical parameters that determine the behavior of the system and estimate their typical size for the UK catchments based on available data. Secondly, we use this data analysis to construct a minimal mathematical model describing a catchment and all the important properties of the flows. Thirdly, we use this benchmark we analyze this benchmark using asymptotic methods to reduce it to as simple form as we can, and to hopefully reconstruct either the scaling curves, which describe the peak flow in peak flow formation, or even analytic solutions. And finally, we can use this benchmark with our analytic or semi-analytic solutions to assess the accuracy, the possible sources of inaccuracy of currently used models, just by checking if the asymptotic behavior predicted by those models is inconsistent with our physical benchmark or not. So the first part will involve understanding the key physical parameters. The governing equations which are describing our flow components are the Richards equation, which describes the subsurface flow. This is nothing else than the continuity equation with the derivative of soil saturation with respect to time. which is equal to the divergence of the flow, which is given by the Darcy's law. So it's proportional to the gradient of pressure times a constant which is called the hydraulic conductivity, which well, it's not necessarily constant because it may depend also on the pressure measured by hydraulic head H here, especially in the unsaturated soil, in which the water doesn't fill all the pores. And the functions here, this theta and k, are highly nonlinear functions of this pressure head H, of our pressure. And this can be modeled, for example, using the Mallen-van Genuten model listed here, written here. The fact that it's highly nonlinear system makes it very difficult to solve, both numerically and even trying to approach it analytically is quite hard task. Secondly, we have an overland flow, for which we usually use the physical models usually use Sandvan's equations, which is again a continuity equation, which is describing the change of height of the ground surface water with time, which is equal to the divergence of the flow, which is given by the so-called Manning's equation. This is an empirical equation relating the h, the height of the surface water, to the flow, and also it includes the square root of the slope as one of the as well as a prefactor here. And finally, we have a source term which includes the rainfall, minus evaporation in general case, minus also infiltration of the water from the overland flow to the subsurface flow, which is for which we need to define some coupling conditions between those governing equations. And in those governing equations, you can see a lot of parameters marked here in red. And as if finding the typical scale of those parameters in the real world systems may allow us to understand the relative importance of all the terms occurring in them. So and it was quite surprising that even though the data describing all those parameters, at least for the UK, are quite easily available and accessible, however, there was not a single a review which tried to summarize all those parameters, which is something that we mathematicians would try to do first of all to do any non-dimensionalization of those models in the next phase. So we looked at the available data sets. For example, we extracted the typical rainfall and evaporation from the data which are shared by the National River Flow Archive, which includes the data about the historical precipitation and river flow for a lot of the catchments in UK, actually for all gauge catchments for which the flow is being measured. We used the Ordnance Survey data, for example, the map of all streams or rivers in UK, to find what is the typical length of the catchment, which we define as the length of the longest stream or the length of the main river, to get a sort of idea of the extent of the valley that we want to model. And secondly, by having the data about all the streams and also having the elevation data from the Ordnance Survey, so-called digital terrain model, we can also find what is the typical value of the slope along the river. Secondly, again, by using the digital terrain map of the terrain, we can also find the typical valley width, so typical of a distance between the rivers, by finding the streamlines going along the steepest descent direction until we reach the river. And by looking at the typical length of those streamlines, we can estimate the width of our catchment, here marked as Lx. Also, by looking at how the elevation of the terrain decreases as we go along the streamlines, we can find also the gradient along the hill slope, gradient perpendicular to the river, approximately perpendicular to the river. So we already have the dimensions, x and y. We also need to know what is the depth of our aquifer. And this is also can be extracted from the data that are shared by the British Geological Survey in the data set called UK 3D, which includes of the three-dimensional profiles of the aquifer, which are obtained by interpolation of the data measured using boreholes, which were digged all over the UK. However, in some places, there is no like productive aquifer. There is no, the rock is almost impenetrable. In which case, the area space which can be occupied by the soil will be by the water will be given by the thickness of the soil, which in case of UK and I guess almost any other place in the world will be of the order of magnitude of 1 meter, which is what this map shows us, also obtained from the British Geological Survey datasets. And the last thing, if we already know how our domain looked like, what's the shape of it, we should look at the proper hydraulic properties of this aquifer, the place where the groundwater is formed, the zone where the groundwater is formed, and we can obtain those from the European Center for some European data center and the data sets 3D soil hydraulic database for Europe at 250 resolution, which includes, for example, the data about hydraulic conductivity and all the other parameters which are occurring in those nonlinear equations that I showed you on when showing the governing equations. And also, but this includes only the data about the soil. We have also the data about the hydraulic conductivity out of the bedrock, but this is not generally available for any place in UK. I just managed to get this estimate by looking at several studies which are conducted in different places all over UK and get some mean value from those studies. So as a result of this part of the project, we found identified the key parameters which are used in the physical models. We found the parameter distribution of our UK catchments for which we had which are specified by the National River Flow Archive. We also listed the data sets from which we can obtain those estimates, together with explaining in the paper very detailed information about how can we reconstruct how those estimates were obtained, and also we plan to share the codes, the source codes, so that it's commonly available. And finally, we also compared the values that we obtained to values which are used by other benchmark studies, which were trying to either take some arbitrary values of these parameters or try to reconstruct them for like one specific catchment, so in a much smaller scale than what we did. So in this way, we managed to sort of standardize all parameters that we should include in the models, and which hopefully will be a starting point for hopefully many other research done in this area. Another interesting thing that we noticed is that we can use the principal component analysis to understand what are the how are different parameters correlated with each other and distributed over the UK. And what we can see that the first two principal components will give us very important information, because the first component will correspond to the topography of the terrain, with low values correspond to lowlands and high values corresponds to the highlands, while the second component will give us important information about the importance of different flow components. So the catchments with low values of the second principal components will have a lower importance of the groundwater, higher importance of the overland flow, while the catchments for high values will have dominating effect of the groundwater flow. If we already know how those catchments work in the real world, what are the typical parameters, we can try to construct a benchmark model, a minimal benchmark model that we can study then mathematically. And we form it in the following way. Let's assume that we have a V-shaped catchment, which is also tilted so that the water will go down the river. which is illustrated on this picture. Here I'm taking some simplifying assumptions that are needed for two purposes. First of all, only if I analyze a simplified geometry, I'll be able to obtain a nice analytic scaling laws. But secondly, the results for those geometries will be very easily interpretable. While when we conduct an analysis on a real world system, we can interpret the results for this specific catchment. But for example, we cannot say, okay, what would happen if we change one parameter at a time? We cannot investigate this effect simply. So, and also if, so the main simplifying assumptions that I have is that we have a uniform slope, both perpendicular along the hill slope and along the river, which is coming from the construction of this geometry. And also I'm assuming that everywhere we have the same aquifer depth, so we have the same thickness of this rock and soil which water can occupy. I'm again, from the construction of this V-shaped catchment, we also have a translational symmetry. So no matter where we put a cross section perpendicular to the river, it will always look the same. And finally, I want to investigate. I want to assume that all properties of the soil and rock material and also the surface of the terrain is uniform. So for example, we have everywhere the same hydraulic conductivity. We have everywhere the same roughness of the surface so that we can fully control them. But it also means that we won't be including the existence of any large-scale fractures or macropores through which the water can flow quicker than through the rest of the soil, which are observed in practice. But excluding these effects allow us to have a model which is easier to interpret and for which we can obtain conclusions easier. So these are the equations that I wrote down in x, y, z coordinates corresponding to the x, y, z coordinates as showed here on this picture. And the standard thing that we mathematicians do is, of course, try to make the model dimensionless. So I'm rescaling x, y, z with the dimensions of my catchment, of my hill slope. Secondly, I'm rescaling the time with some typical time scale equal to Lz over k, which is a time scale that allows me to balance the two dominating terms in the Richards equation for the groundwater. So it allows me to balance the effect of these two terms, which often seem to be dominating ones. Secondly, I'm rescaling rainfall with some typical values of the rainfall, mean values of the rainfall in a given area. I rescale Hg, the hydraulic head describing the groundwater flow with Lz, which is the highest value that the pressure can reach at the bottom of the aquifer in a steady state. And I rescale with the surface height, Hs, with H0 in order to balance the two terms marked in blue in the second equation, which would correspond to, which will be the typical height of the surface water in a steady state. So by doing this non-dimensionalization, I'm obtaining the following equations in which we have 4 packs of the dimensional parameters, which are forming 4 dimensionless quantities, which are called beta x, beta y, tau s, and xi. And thanks to the fact that we have this table available for all the catchments of all the typical parameters representing them, we can find what are the typical values of these dimensionless parameters beta x, beta y, tau s, and xi. And these are the following. And we can learn 2 very important things from these parameters, from their typical sizes. First of all, since beta y is very small, the second term in this equation will be smaller by like 3 orders of magnitude comparing to the leading terms. So we can in the first order of approximation we can get rid of this term or investigate the effect of the small beta y on the solution of the full 3-dimensional problem. The second thing that we can observe is that psi is also approximately 3 orders of magnitude smaller than the leading terms here. So you can also get rid of this term. It may be tempting to take the tau as also very small and get rid of this term, but this term is quite important in a very short times after the rainfall, because it describes how quickly the overland flow will reach the new steady state. So I'm keeping this term. But by removing these two terms, you can also notice something interesting. I removed all terms which include some variation in y, which means that our 3D problem, for which the solution h, s, and hg depends on x, y, and z, can be reduced to a two-dimensional problem, as long as these two this should be psi, sorry about that. As long as these two parameters were very small, we can reduce it to two-dimensional problem. It depends only on x and z. We got rid of y dependence, which makes this model already much simpler to analyze numerically, and hopefully we can reduce it even further and learn something from it analytically as well. But before I go to the analytic work that we did, I'll just tell you in a few words about how can we investigate this two-dimensional model numerically. For this purpose, we developed a finite volume solver, which is solving the coupled groundwater and overland flow equations. We do this sequentially. I'll tell you in a second why. In the first step, we are solving only the groundwater flow in this gray and yellow zone by using an implicit scheme, implicit solver, in which in each step of this implicit procedure, I'm linearizing these nonlinear functions theta and k linearly around the current value of h, as compared in the previous iteration step. And in this way, I'm getting a linear system with respect to h, which I can solve using standard linear solvers for h, and I continue this procedure until I reach some more or less steady value, unless the error is smaller than a given threshold. In the second step, I'm using the solution of this groundwater to find how quickly the water will accumulate on the surface, and use it as a source term for a solver which is an implicit solver for solving the overland equations, but I don't solve the overland flow with the same time step as the groundwater flow, but I divide this time step into multiple short intervals. Why I'm doing that? Because overland, characteristic time of the overland is usually 3 orders of magnitude shorter than the typical timescale of the groundwater. So I divide into multiple time steps so that I can have a one long step for the groundwater, which is very demanding computationally because of the fact that the equation for the groundwater is 3-dimensional equation, and the equation for the overland flow is only a 2-dimensional equation. So this allows me to find the most precise result in as reasonable time as possible. And thanks to this solver, we can do a lot of experiments investigating how. Yes, sure.
You're asking for this solver, you wrote a full 3-dimensional one, so you're including all the terms.
I wrote a solver which is fully 3-dimensional, but you can make it 2-dimensional just by setting ny number of elements along y direction to 1, which will give me a 1-dimensional solver. Yeah, but we wanted to have also 3-dimensional solver just to check if our approximations of 3-dimensional geometry with 2-dimensional geometry make sense. But in 2-dimensional geometry, again, it's good to divide into 2 steps because now the groundwater problem is 2-dimensional and the surface flow is 1-dimensional. So it's still good to separate these 2 components.
Can I ask another question? It's something that's slightly confusing me.
Mm-hmm.
If you have something that's a valley like this, I can understand that the flow in some sense looks very similar at different cross sections, but you would imagine that the discharge accumulates along Y.
It accumulates.
So that the discharge doesn't is not independent of water.
Yeah, it accumulates, but it doesn't accumulate significantly in the soil and in the bedrock. It's mostly accumulating in the river, and the river is transferring this very, very quickly to the outlet. Here, I'm modeling only what's happening in the soil and on the surface. I'm not including the equation for the river in this approach. Yeah, I'm just saying that. That I want to find what is the inflow of the groundwater and of the surface water to the river, which then can feed another one-dimensional model. Yes, it doesn't include the river. This river takes the whole water out of the system. I should have mentioned that. Sorry about that. And thanks for the question. Yeah, so thanks to having this numerical solver, we can see what is the effect of the different parameters that we found on the flow. And here on a simple example, we can see that decreasing the cell conductivity leads to a very interesting jump in the peak flow that we observe when the hydraulic conductivity is not high enough to transfer all the water through the groundwater in the root. That at some point when we have very low soil conductivity, the surface water start to appear, which is marked by red peaks here, which is causing the peak flow after the rainfall to be much higher than the peak flow that we had for high conductive aquifers. And we can investigate the other parameters in a similar way and try to systematize it and get some scaling law even numerically from this model. So another interesting thing that we can learn from the effect of the from the reduction of three-dimensional model into two-dimensional model is the fact that we should be able to write down that the flow coming to the river it's the same in all the cross sections. So the total flow in the river should be proportional to the length of our river, to the length of our valley, as long as the flow in all the cross sections is identical in flow to the river. However, the statistical models that are currently being used suggest that they are taking area as our area of the catchment as the independent parameter from which we try to deduce what will be the peak flow observed after the rainfall. However, the effect of the length and the width, according to our physical model, may be completely different, and we cannot just group them into a single parameter called area. And just to show you the potential of such analysis, I try to compare two statistical models. One in which I'm taking only area as as an independent argument parameter, and the second model in which I take width of the catchment, length of the catchment separately as two independent parameters, potential independent parameters. And we can learn three exciting things from this model. First of all, that indeed it seems like the flow is proportional to the length of the catchment. If you don't see, there's an exponent of 0.99. So the flow is basically proportional to the length within the confidence interval. Secondly, the fit quality also increased. That just that the R squared value rose from 0.48 to 0.59. And finally, if you look at typical statistical model diagnostics, we can see that in the original model, if you include only area as the parameter, as an independent parameter, the errors won't follow the normal distribution, what we can observe on this QQ plot. While in case of the model which is reading width and length separately, this the distribution of the errors is much closer to what we expect to see in statistical models. So the physical model here informs us of some scaling law, which after introducing to a very simple statistical model, allow to improve it significantly, which is a nice case that I like to show to show how useful such analysis can be in practice. But of course, in practice, the statistical methods currently being used are using area as one of the parameters. There are also some other parameters that I'm not including here because I'm still investigating the effects of other parameters. And the good question would be, to ask would be, can we go even further? Can we go beyond only like numerical investigation of this two-dimensional slice? And it turns out that we can. We can make a one-dimensional model even, but not in a general case. In general case, it's not possible, but it's possible in the areas, in the river catchments, in which there is no groundwater. So we don't have this full three-dimensional structure under the ground. These are the catchments in which the flow reaches the river in two ways, either as a surface flow or as a subsurface flow, but only through a very thin layer of soil located just under the ground. In such case, the beta X parameter, which is comparing the typical extent scale in Z dimension to the typical scale in X dimension, is very small, and we can reduce the system in such case from a two-dimensional problem of quite deep geometry into two-dimensional problem in very thin geometry, which then can be also reduced using so-called Boussinesq approximation to a one-dimensional equation. And in this last part of this talk, I just want to outline you how this one-dimensional model is constructed and how it allowed us to find analytic equation for the hydrographs for those catchments with impenetrable bedrock, with the whole flow only going through a thin layer of the soil. And so this is our geometry. Do we have a thin layer of the soil? I am already producing we'll write down the dimensionless model so that just to save time, I don't have much time left, I know. And in this, again, the source term is provided by the rainfall. Here we're written in the using a dimensionless, represented using a dimensionless quantity rho. And this rainfall is causing groundwater to develop in the soil, which is described again by the Darcy's law, which includes both flow, which is caused by the gravity, and the flow, which is caused by the gradient of pressure, by the gradient of the height of this water, which is creating a gradient of pressure. And if we have only as a groundwater, if we have only a groundwater flow, we can write the continuity equation, which will describe as the variation of hg, the height of the groundwater, with time, as divergence of the flow of the groundwater plus a source term representing the rainfall. However, when the groundwater reaches the surface, it cannot go even further. It will create an overland flow, for which we'll have slightly different governing equations. This time, the groundwater is given by the same equation as before, but hg will be equal to 1 because we scaled the thickness of the soil to 1. And secondly, we'll have an overland flow, which according to the Manning's law that I mentioned some time ago, is just proportional to h, to the surface flow, to some power of k. And the governing equation for this saturated zone will be the same one as before, but this time for the flow will take the sum of these two components. The equation that you see above can be also derived from this two-dimensional model. I try to explain it in more intuitive way so that you can see what is the interpretation of this model, which is much simpler to understand than the full two-dimensional or three-dimensional model. Additionally, here we have an interface, which will say that is located at point A, in which to have the continuity of the flow, in order to have the same flow reaching this point from the right as the flow going to the left, this condition results in the continuity of h, g, and hs in this point. The derivative of hg need to be equal to the derivative of hs, which is creating a coupling between the saturated and unsaturated zone. Of course, hs at this point is 0 because the surface voltage disappears here, and hg is equal to 1 because the groundwater reaches the surface. This is the already well-defined mathematical model as well. I should also include some boundary condition at the end. There is no flow here, and there is free boundary condition here, free flow boundary condition here. But this allows me to, let's go back. This allows me to find how the groundwater and the surface water will evolve in time. However, this picture is not fully properly representing how the relation between the height of the surface water and the groundwater, because the surface water in practice is very, very small, as long as this mu parameter is very large. So in practice, the solution may look like that. This is the solution that we obtain for the typical catchment parameters, the one extracted from the available data sets in part 1. And it seems like there is almost, these are the equations that I obtained just by integrating the governing equations, the governing PDs with respect to X. And it seems like there is no overland water at all. There is one, but it's very small. We can see it, for example, by zooming this area. We can see that the groundwater is emerging from the surfaces, create very, very thin surface water. Okay. The one thing that we analyze is the steady state, because we wanted to take a steady state as our initial state in the simulation, steady state of the groundwater for some mean rainfall, and then see what happens if we turn on a more intensive rainfall. Okay, can we see how a more intensive rainfall turned on turned on at some point, how would it affect the flow that we observe in the river? So in other words, what will be the hydrograph of the river flow when we turn on an intensive rainfall starting from steady state conditions? Let me skip some technicalities. How much time do I have? Not much, so let me skip some things.
5 minutes, 10 minutes tops.
Yeah, if you are interested in technicalities, I can explain it to you later. This is the idea that we start from the steady state and we develop a time-dependent solution for the rainfall. What we can say, what we can learn when we look at the numerics, is that the groundwater, which is represented by these colorful lines for different moments in time, will be slowly rising during an intensive rainfall. This is something that we should expect. As the groundwater is rising upwards, it will also move the interface between the saturated zone and unsaturated zone to the right. And at the limit, where maybe I'll show it in a moment. Do I show it? No, I don't show it. Okay, at the limit when the I don't want to go into technicalities too far since I don't have much time. We can consider a short time limit because the typical timescale of the groundwater is approximately 1,000 days, is the sort of magnitude. While let's be honest, even in UK we don't have the rain which takes 1,000 days. So we will be rather interested in the short time behavior of this groundwater. We can find the outer solution for this groundwater, which is the following. This is the short time solution. So the groundwater will just go upwards linearly, proportionally to the time which passed, and proportionally to the difference of the current rainfall and the initial rainfall. As it goes upwards, we can find the cross section of this solution with the value h equal to 1, the groundwater height equal to 1, which will give us some estimate of the location of the interface between the unsaturated zone and saturated zone. We do this rigorously, so we investigate some boundary effects here, but the general idea is as I explained. Since the shape of the groundwater around this interface initially can be approximated as a quadratic function with no linear term, we can find an analytic expression for the time that is needed for this front to travel a distance x0 from its starting location. So it informs me how quickly this the saturation zone will increase with time. If we already know that, we can try solving the overland equations, but for the overland flow, the typical timescale of overland flow is about 2 hours. So I cannot say that the rainfall events that we are interested in are shorter than that. We need to find the solution for all possible times. But luckily we can do this thanks to the fact that in practice, okay, let's do a quick rescaling. In practice, if we non-dimensionalize this, well, if we pick a proper timescale for our time and proper scale for our age, we can derive the following equation in which there is a dimensionless parameters called the Pecklet number, which is telling us what is the relative importance of the diffusion term to the of the convection term to the diffusion term. And in practice, this Pecklet number is extremely large. It's like 10 to the 5th. So Pecklet to number to the power of -1 will be something like 10 to the -5, which allows me to, at the leading term, to get rid of this term. Oh, I thought there would be, oh yeah, that's what I wanted. Which will allow me to get rid of this term. And what I'm left with a PDE, first order PDE, non-linear PDE, which can be solved using a standard method of characteristics, in which the characteristics lines will start either from the initially saturated zone and will rise because of the increased rainfall, or will start from the propagating flow, which is slowly moving to the right, away from the river. And by solving this problem, this PDE in these two regions for these two initial conditions, we can find the flow at any time, which is quite amazing. Again, clipping through all the derivations, but what we get in the end is we can find how the height of the surface water changes with time, we can convert the height of the surface water into the surface flow into the river, which is proportional to h to this power 5/3. And I can find an analytic formula for dependence between T and Q, the time and the flow in the river that will reach after a given time, which is expressed as follows. The only problem is that it's not that easy that it's like an implicit formula for Q. We don't like implicit formulas. I mean, they are fine, but if we can find an explicit formula, that is even better. But it turns out that we can find an explicit form after some additional but very realistic simplifications by analyzing only, again, a short time solution with respect to the groundwater timescale, which allows me to also find this hydrograph nicely analytically in an explicit way. And here on this graph, you have comparison between numerical solution marked in blue with a blue line, with analytic solutions marked with a red line and a yellow line, which are extremely close to each other, with the only difference that the red solution is the implicit solution and the yellow one is the explicit solution. So one is given by this equation and the second is given by this equation. But no matter what approximation I'm using, I'm still very, very close to the full solution of the original numerical PDE, which is something that I wanted to obtain. And now, since we have this benchmark hydrograph, we can compare whether other models than our physical model, like database models based on this dynamic system or statistical models, whether they will predict similar behavior of the system, similar scaling laws, by describing Q as a function of all the catchment parameters that you can see here. So this is how we reach the conclusions. We managed to successfully build a minimal toy model of a catchment, which is including both effects of the groundwater and overland flow coupled with each other. which is describing this tilted V-shaped valley. Secondly, we managed to use mathematical methods like non-dimensionalization and static analysis to reduce this three-dimensional model into two-dimensional form, and then one-dimensional form in certain scenarios, which we are able to solve either numerically or even analytically in certain situations. And finally, finally, we hope to try to use those benchmarks that we developed to assess whether first of all, to check if they are consistent with the data that we have available for UK, to have some evidence that our benchmark scenario is representing at some extent the real systems. And secondly, we would like to provide a detailed comparison of this benchmark model with other models which are currently being used in UK, and possibly point what are the possible sources of what are the possible of inaccuracy of differences between the results, and whether we can somehow improve the existing models, which is some long-term next goal that we hope that our research will allow to do in the future. But keep in mind that since I'm developing all the theories based on simple benchmark scenarios, which are oversimplifying the reality in some extent, any modification, any suggestion for the modification of the procedures for flood estimation has to be done also numerically on the real world data. So I'm not saying that this analytic approach will is the thing that how we should develop models. It's rather an idea as a complement. I treat it as a complementary tool to the numerical analysis, which is done by hydrologists to confirm whether the models that we are using gives reasonable answers for the data that we have available. And I hope it will, but still I hope that this analytic approach, more rigorous approach, will allow us to help while solving the issues with which the current methodologies are coping with. And also I think that this is very fascinating area for mathematical research, which is completely underrepresented in the mathematical community. Thank you a lot.
Trying to come in at the moment. Do we have one very quick question?
So you would use the model from 3D to 3D parameters or base models. You also said you assume symmetry in the Y translation. Doesn't that effectively already mean that your model is two-dimensional?
Sure. Not really. Let me go to the valley slide. Not really, because it's not a valley which looks. It's like a V-shaped valley, but it's tilted. So there's also some slope along the Y direction, which will be forcing the water, both the groundwater and the surface water, to travel perpendicularly to the XY plane, which is illustrated here by this profile. So since the whole valley is shifted downwards, the water will tend to flow downwards. But as long as the slope in Y direction is small and the extent of my valley in the Y direction is large, then these flow components, which are perpendicular to the hill slope, will be negligible small. And that's when I can reduce the model to 2D.
Thanks so much. I think we better stop there.
I'm happy to answer any of your questions after we leave the room.
Yes.
If needed.
Well, thank you very much.
Thanks a lot.